Hi, I'm Manny with Artha Engineering. Welcome to our motor controller demonstration video. What we have over here on the left is Artha Engineering's very first proof of concept motor controller. And what our motor controller does is to supply an electric motor with enough power to maintain speed under varying load conditions. So when you have any kind of situation where a motor is underutilized or underloaded, we can reduce power to that motor while not slowing it down so that it can continue to do the work that it needs to do, but use less energy. So what we have here is a watt meter that supplies power to the motor controller, and then out of the motor controller, via this orange cord, we supply power to the motor. And those are the only connections to the motor. So there's no sensors or feedback circuits or anything extraneous, just AC power in, power out to the motor, and the motor controller, which is purely analog. There's no microprocessors or anything like that. So the underlying technology is a very robust analog technology. Simply supplies the electric motor with enough power to do the work being required of it on an instantaneous basis. So in this demo, the motor that we're using is a little 1/3 horsepower single-phase electric motor, and it's driving this car alternator. And the alternator in turn supplies electricity to light these headlights. Now, an alternator needs a current source in order to generate electricity, and in a car that would come from a battery. Now if you don't know exactly how an alternator works, you need to go Google that because I'm not going to get into it here, but we're replacing the car battery with a bench supply, and so by simply turning a knob I can vary the amount of current being supplied to the coils in the alternator, which in turn enables the alternator to generate more or less electricity, which makes the lights go brighter or dimmer and varies the load on the motor. And then we can monitor how much power the whole system is using to do this through the watt meter and see what kind of energy savings we get. What I'll do, of course, is to engage and disengage the motor controller so we can see these differences as we change the load on the motor. For the first part of our demonstration, I've got the belt off of the motor, so the motor is not doing any work, it's just going to spin. And the motor controller will be engaged, and we'll be able to look at the watt meter and see how much energy it takes with the Artha Engineering motor controller, just spinning the motor. And then what I'll do is, with this clip lead, is short out the motor controller, basically shorting the incoming power to the outgoing line to load, so that we are not controlling the motor, we're just supplying it with AC out of the wall, and we can compare readings on the watt meter in both cases to see the energy savings. So the first thing I'm going to do is switch the motor on with the motor controller engaged, just like that. Now our motor is spinning, there's no belt connected of course, and it takes about 162 watts to make the motor spin in this condition. Now I'm going to short out the motor controller so that we're just supplying straight AC right to the motor. And now we see that we're drawing 322 watts to do the same job that we were doing before with 162 watts. So now I've got the belt on, so the motor is driving the alternator, but I am not supplying any current from the bench supply yet, so the alternator is not going to generate any electricity and the lights are not going to light. The alternator, of course, is out of an automobile and would normally be hooked up to at least a 100 horsepower motor, and we have a 1/3 horsepower motor. So this, just spinning this alternator, not generating any electricity, represents a substantial load for this motor. Probably about 75% of its capability will be used just to spin this, not generating electricity. So I'm going to turn it on. And so the motor controller is engaged, and we are using approximately 228 watts to spin the alternator, not generating electricity. And now I'm going to short it out once again, take a reading, and we're up to approximately 355 watts to do the same work that we were doing just a moment ago. Not as big a difference as we had before in the unloaded motor case, because as we increase the load on the motor itself becomes more efficient, and that's part of what we're demonstrating. But still quite a substantial savings for this 75% load on this motor. Now we're going to supply the alternator with some current so we can get a faint little glow out of the lights and increase the load on the motor even further. So let's turn it on. There we go. And now I'm going to go to 1 amp. There we go. So we've got the faintest of glow in the headlight, and we are drawing 268 watts roughly to do this amount of work. Now once again, I'm going to short out the motor controller so that we're supplying AC out of the wall directly to the motor. And there we have 359 watts. So a substantial increase, not quite as much because we're getting more efficient as we increase the load. Next, we're going to add even more current to the alternator so that it does even more work. And last time we had 1 amp of current to the alternator, so now we're going to go to 1.5. And at 1.5 amps to the alternator, we've got a nice little glow in the headlights. And to do this work, we're requiring approximately 325 watts out of the wall. Now, once again, I'm going to short the motor controller out so that we're just taking AC out of the wall directly to the motor. And power usage has gone up to roughly 373 watts on average. So increase in power usage, but the difference is getting smaller as we approach 100% of load for the motor. The final step in our demo is to increase the current to the alternator so that we fully load the motor. So we were up somewhere above 90% of the rated load capability of the motor. And at that point, we'll see that there's no energy savings because it's as efficient as electric motors get in that condition. Now, the thing to remember is that electric motors are almost always oversized. Engineers always overspec the motor so that they last longer and margins of error and all that. So the potential to save energy in common usage of motors of this type is huge. So let's get on with the demo and we'll demonstrate this. So we'll turn this on. Turn this up to, we're going to go to 2 amps now. There we are, 2 amps. So now we've got really bright glow out of the headlights. And we're using approximately 395 watts to do this amount of work. And one last time, I'm going to short out the motor controller and supply the motor with AC power out of the wall. And we're at 403 watts. So hardly any difference at all at this point because the motor's as efficient as it gets. So that concludes our demonstration. Thank you very much for watching, and email us with questions.